Hello everyone. The topic that we are going to discuss today is SISO shift register. So first of all, to understand SISO shift register, first let us discuss what is a register. Then we'll discuss what is a shift register. Then we'll go into the details of SISO shift register. Okay, so first of all, register. Register is simply collection of flip-flops. A register is simply collection of flip-flops taken together as a single entity. For example, 4 flip-flops together form a 4-bit register. 8 flip-flops together form 8-bit registers. Okay, so what is the function? It is to store information or hold information within a digital system so that it is available to the logic elements during the computing process. Okay. For example, any computation, there are some intermediate results that you may have to store, right? Or final results you will have to store. To store information, you make use of the registers. Okay. Then each combination of stored information is the content of the register. For example, 4-bit register. Okay, so you want to store result of say binary addition of 3 plus 2, which is 5. So the contents of the 4-bit register after the addition can be this. Okay, the equivalent of 5 is in binary form, it is 0101. Okay, fine. So to store such an information, we can make use of the registers. Then we will go for, so far I hope everyone have understood what is the register. It is combination of flip-flops to store information in simple words. Now what we will see is, we will see what is a shift register. Okay. So registers that are capable of moving information upon the occurrence of clock signal. So once a clock signal is given, the information moves from one flip-flop to the other, okay, inside the register. So now the movement of information can be one direction. It is called as unidirectional, or it can be in both ways, in forward direction as well as reverse direction. Okay, fine. Such a register where the movement of information takes place in both directions is known as a bidirectional shift register. And a register in which the movement of information takes place in only one direction, okay, say left to right, such a register is known as a unidirectional shift register. So now, two basic ways in which information can be entered or outputted into a register. There are two ways in which you can enter the information or you can take out the information. Okay, first one is parallel, second one is serial. What do you mean by parallel? All the symbols, now remember we are dealing with binary data. Okay, binary means it could be 0 or 1, so only 2 symbols. All the symbols are handled simultaneously. Handled means it could be entered simultaneously or it could be outputted simultaneously. Okay, fine. Such a condition is known as parallel. So then it requires as many lines as symbols. Means if you want to insert 4-bit of information, okay, through parallel lines, then what we need? We need 4 lines. Okay, right? So as many symbols that you want to insert, those many lines are required. Okay, fine. Then what do you mean by serial? Symbol by symbol. Okay, fine. So let us take simple examples. A parallel, if you want to talk about the entering data inside the registers parallelly, then what you do? This is how you enter. Okay, fine. A register is combination of flip-flops. So these are your flip-flops. I have drawn 4 flip-flops, and then you enter data all together. Such an entry is known as parallel entry. If you have again say 4 flip-flops and if you enter data at one end only, okay, if you enter say data at one end only and this output acts as input to this and this output acts as input to this and this flip-flop output acts as input to the next flip-flop, okay, such a situation is known as serial entry of data. Such a situation is known as serial entry of data. And here when you have 4 lines of data entering into the flip-flops, okay, fine, such a condition is known as the parallel entry of data. So, one line enters here, another line enters here, another line enters here, another line enters here, okay, fine. Now, what we will do is, see, we have seen serial entry, we have seen parallel entry of data into the registers, okay. So, now when it comes to registers, there are 4 possible registers that you can have. One is serial input, serial output, okay. Both the entry of the data into the register as well as taking out of the data from the registers, both is in serial fashion. Input in serial, output in parallel, okay. Such a register is known as serial in parallel out, okay. So, this is your SISO shift register and this is your serial input parallel output shift register and this is parallel input parallel output shift register, okay. Next one will be parallel input serial output, parallel input serial output shift register, okay. So, now we are going to see the serial input serial output, which is SISO shift register. So, this is the circuit diagram of 4-bit SISO shift register. Fine, as we have discussed, you have flip-flops. Each flip-flop can store 1 bit of information. So, 4 flip-flops together, they can store 4 bits of information. So, this is a 4-bit 1, 2, 3, 4, okay, 1, 2, 3, 4, 4 registers, right, hence 4-bit SISO. Why SISO? SISO stands for serial input, serial output. Data is entered serially, it goes serially, it goes serially, it goes serially and it is also outputted serially, fine. Hence, the name of the register SISO shift register because of 4 bits, 4-bit SISO shift register, okay. Now, here what we will do is, let us say if you want to insert this data 1 1 1 1 means initially all the outputs are zeros, okay, fine. This is how we assume in a shift register, initially all the outputs we take 0. So, initially all the outputs, so here we are taking D flip flop, fine, and we are labeling it D0, D1, D2, D3, likewise Q0, Q1, Q2, Q3, flip flop 0, 1, 2, 3. I hope it is very simple. Then what we will do is, initially all the 4 outputs we will take it as zeros, okay. Now, there are different types of flip flops, the way you trigger them, okay. Now, here we are considering the falling edge triggering, okay, which is very simple, fine. When you have a falling edge, then the transition of the signal takes place. Like in this case, when there is a falling edge, then only the transition of the output signal takes place, only at the falling edge, okay, fine. So, now what we will do is, let us consider say first falling edge, edge, what happens? Means, see now task is this. We are going to give 1 first. Okay, right? So when you have first falling edge, fine, then what happens? This is activated, this is activated, this is activated, this is activated. Okay, fine. But remember, all the initial values are at the output, all the initial values are zeros. Initially, all the values are zeros. Okay, fine. When you have 1 here and you give a clock signal, then what happens? This 1 comes here. Okay, right? Simultaneously, what happens? This 0 goes there. Fine. And this previous 0 goes here. And this previous 0 goes here. Fine. Then the output will be 1 0 0 0. The output will be 1 0 0. Okay. Now the situation is like this. At the end of first falling edge, we have 1 0 0 0. Now let us say you give one more 1. Okay, you give one more 1. Now what is the situation? Now again for the second falling edge, every bit will shift 1 step towards right simultaneously. What does it mean? This 0 is taken out, this 0 shifts here, this 0 shifts here, this 1 shifts here. Okay, this 1 shifts here. Fine. So as a result, let me write the output. So this 1 comes here. So this is no longer 1, this is 1, and this 1 comes here. Okay, so you have a 1 here, this 0 comes here. Okay, fine. So you have a 0 here, this 0 comes here, you have a 0 here. So at the end of the second falling edge, the output is 1 1 0 0. Fine. Now we have discussed for 2 cases. Now one more clock pulse. Okay, one more clock pulse. Each value shifts towards right, and remember we are giving again input as 1. Fine. So in such a case, what are we supposed to get? We are supposed to get 3 ones and then a 0, and that is what we have. And when you give the last one also, right, what is the situation? Now all the 4 outputs become 1. I hope the logic is very simple. Okay, so what we are doing, initially all are zeros here, and we are entering 1 by 1 value simultaneously, serially. Okay, 1 by 1 value we are entering serially. Fine. So as a result, what happens? So initially you have 1 0 0 because of the 1 entry. Okay, and then next case you have 1 1 0 0, next 1 1 0, and then okay 1 1 1 1. So it takes 4 clock pulses to enter a 4-bit data into a 4-bit shift register. So in general it takes n clock pulses to serially enter the data into a shift register, into a n-bit shift register. It takes n clock pulses. Okay, now we can also have the waveform representation of the 4-bit SISO shift register. Okay, fine. So what you can do, just you can look at the table which we have seen in the previous slide. Okay, so initially all the Q0, okay, Q0, Q1, Q2, Q3 all are zeros initially. Okay, so initially, fine, initially all are zeros. Fine. Now the input we are giving here, the input we are giving there. So when you give input, now remember that the input should be available before the clock pulse arrives. and we have discussed that we are considering the falling edge, okay, right, we are considering the falling edge. So suppose in this case this is the rising edge because signal is rising here, okay, and this one will be the falling edge because the signal is falling there. Okay, so initially we have all Q3, Q2, Q1, Q0 zeros. Now the input should come before the arrival of the falling clock pulse, and when the input, okay, when the input, right, here what is the case, input is changing from 0 to 1, and then we have a falling edge, right. So what happens here, now the Q3 transitions from 0 to 1. I hope you remember in the previous slide, this one we have written here, okay, fine, when we have a clock pulse and that transition is indicated here, fine. Now remember Q3 remains 1 1 1 1, okay, in all the cases according to the previous table. If you see, for every clock pulse Q3 remains 1, so every clock pulse Q3 remains 1. So this is one easy method. From the table you can easily get the waveform representation or timing diagram. How we can get? Just the table here, what you are doing, you are drawing the table like this. The same thing you represent like this. For example, what do you have here? 1 1 1 1. What did you have there? 1 1 1 1 given vertically. Now we are giving that horizontally. Next 0 1 1 1, okay. Next 0 1 1 1, right. Next 0 0 1 1. So next 0 0 1 1. So 0 indicates by low pulse. Initially all the values are zeros, correct. So initially also you have low pulse, and 1 is indicated by high pulse. 0 by low pulse, 1 by high pulse, fine. And let us see Q0. What is the situation for Q0? 0 0 0 1. So 0 0 0 1. Okay, so in this manner easily you can convert the truth table to the waveform representation. Okay, so I hope students are able to understand the 4-bit SISO shift register, how the data shifts within the register serially, hence the name serial input serial output shift register. And we have seen the truth table of this, we have also seen the waveform representation. Now we will see the important applications of SISO shift register. So it is useful in data storage and retrieval. We have seen if you want to store 1 1 1 1, you can enter the data serially and the data is stored. Then next, for instance in communication systems, okay, like for example, if you want to transmit the signal of television, okay, fine, say TV audio signal or video signal you want to transmit. Then you have a cable, you transmit the data serially. In between, if you want to temporarily store, you can use this serial input serial output shift register and we can store it temporarily. Next, if you see the circuit diagram of serial to parallel, okay, fine. If you see the, in fact, if you see the circuit diagram of SIPO, serial input parallel output shift register, what you have is, you have the same, you have the very much same connections here. This is not going to change. The only thing that we will have in addition is, we will have 4 outputs, 1, 2, 3, 4. So just we take only 3 extra lines, 1, 2, 3, okay, fine. So that is the difference between the SISO shift register and SIPO shift register. In SISO shift register, we cannot access the intermediate results. We cannot access what is the output of Q3, we cannot access. What is the output of Q2, we cannot access. Output of Q1, we cannot access. Only the output of Q0 we can access in SISO shift register. But in SIPO shift register, in SIPO shift register, we can access, we have extra lines in these cases. Okay, fine, we have extra lines in these cases. 4 outputs are provided. Q0, 4 outputs are provided. What are the 4 outputs? Q0, Q1, Q0, Q1, Q2, Q3. That is why you have parallel output. Okay, so serial input is not going to change. The data is going to enter serially and the outputs are taken parallelly. So just 3 extra wires within the internal structure of SISO gives us SIPO. And hence we have the application serial to parallel conversion. Okay, you can have by considering some additional circuitry. In this case, to convert SISO to SIPO, you just need 3 extra output wired connections. Next, now if you see in a shift register, the data is entering serially and according to the timing diagram, there is a clock pulse, there is a time duration that is involved. Now in electronic circuits, timing is very important. For example, you are able to see this display because the information is sent, of course, serially, fine, and what happens is the information, for example, you are seeing this screen, okay, the every bit information on the screen is simultaneously displayed, okay, fine, and there is a synchronization, there is a timing that is involved, because of which you are able to see this display clearly. Otherwise, if there is any mismatch, you cannot see the video with this precision. Hence, timing plays an important role in your electronic circuits. And here we are dealing with the time, how much delay you want, okay, how much delay you want. That can be achieved by considering the D flip-flop. D flip-flop simply stands for delay flip-flop. Output is same as input, but it comes after delay, which is decided by your clock signal. So, another application is delay and time sequence generation, okay, generation of delayed versions of a signal of, say, you have different signals, you can generate the delayed version of such signals. Another important application is divided by 2. We have seen that you can store data into the shift register. For example, say, let us say that we have stored here the output is suppose 1, 0, 0, 0. Now at the end of, if you give clock pulse with input 0 here, then what is the situation? This 1, 0, 0, 0 is converted into, it is shifted right and we have 0, 1, 0, 0. If you see, the equivalent of this is 8. The decimal equivalent of 1,000 is 8 and this is 4. So what is happening? It is getting divided by 2. Again, this if you shift right, you have 0, 0, 1, 0. Again, if you shift this one right, okay, you have 0, 0, 1, 0, which is nothing but 2. So how are we getting that? 4 by 2, we are getting 2. Okay, 4 by 2, we are getting 2. So by shifting right, you can have the operation of divide by 2. So another important application of your SISO shift register is divide by 2. Next, it is also useful in digital signal processing where sequential processing of data is required. You want to process the data one after the other. Processing, it could be addition, multiplication, filtering, any digital signal processing. Okay, because the data is entered serially and serially it is outputted, you can sequentially process the data. And what you can do is, you can have some interesting feedback connections. Okay, in such a case, the SISO shift register will keep on running its own sequence. Okay, for example, if I run such a sequence 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, what am I doing? I am counting from 0 to 3. Fine. So, an important application of your SISO shift register is counter, and we can develop by connecting the output back to the input. So, these are the applications of your SISO shift register. In today's class, we have seen what is a register, we have seen shift registers, we have seen SISO shift registers, we have seen the applications of SISO shift registers. Thank you.